let me start with three observations on the particle physics approach to GR. Historical observation. There have always been some incorporation attempts of gravity into particle physics, at least since the early heydays of relativistic particle physics. Yet, it's still no textbook mainstream. There are, of course, these famous exceptions, Feynman's lectures on gravitation, Weinberg's book from 1972, and also, for instance, string theory book by Ortin, but that's about it. Relatedly, sociologically, historically speaking, we have this schism. So we have this GR camp on the one hand, particle physics camp on the other hand, which also gets inherited into how we approach quantum gravity. This has always been like this, and this keeps on being like this. And then the third observation, the conceptual one, there seems to be an uncontroversial sense of particle physics approach for everyone, perturbative view of GR, if you want, in the sense of regime-specific flat space-time thinking, how to think of linearized GR, let's say, in this quantization. At the same time, there are all forms of derivations, claims floating around. We speak to the so-called particle physics approach on top of that. And what I would like to discuss with you, assess with you, is what is their import. So when I say particle physics approach, I will often also say spin 2, because we do particle physics. We happen to do this in flat spacetime, at least traditionally, with respect to the Poincare group, with respect to the spin classification. So the spin S mass M field is that what transforms according to some irreducible representation of the Poincare group. And so it's standard to say things like GR is a spin 2 theory in the sense that it's flat spacetime expansion, so flat spacetime linearized GR, massless phase Pauli is spin 2. It's standard also to say that under certain conditions, a unique generalization of a massless spin 2 theory into an interacting theory, so-called interacting spin 2s, is GR as well. So none of these kind of technical claims will be contested. So I think these are, these two senses of talking about GR as spin 2, maybe in the limit, in the sense of being a unique generalization under certain conditions. These are just technical results which are as they stand. You can argue, of course, about semantics. Is something spin 2 just, so to speak, with respect to a certain kind of Poincare symmetry background, or and so on and so forth. But as they are, these claims stand. I'm much more interested in this kind of conceptual, more general philosophical take we have on these results. So what I'm going to do is the following. I want to sketch what's traditionally labeled the particle physics approach a bit more in detail for you. Then I want to demonstrate by looking at, quite a big collection of quotes. I want to demonstrate the diversity in conceptual readings out there. And then thirdly, I want to proceed more systematically and reconstruct and assess in particular ontological readings. Okay. I have the following thesis. So I want to make first a distinction between epistemological readings of spin 2 approach, of the particle physics approach. So they are just about this approach is just about getting to know GR, just about learning GR, and ontological approaches. So they're about somehow reading an undergirding of GR into this approach. You somehow say the way how you normally think of GR is not fundamental, there's something beyond, and what is beyond that is told to you by particle physics. So within the regime of GR, though, yeah? So no doubt, of course, we will explore more physics after GR, no matter what our discussion of the spin 2 is. But on this kind of ontological approaches, there is somehow a reconceptualization of what GR is about fundamentally. And then what I want to do is I want to argue against ontological readings and thereby make, so to speak, a case for the epistemological readings. Now everything is a footnote to Plato. So here, in the so-called cave allegory, you ascend from the cave where you just had all these illusions and shadows, right? And you go towards the light. And the big question for us is, so to speak, for the spin 2 approach, is this just an epistemic ascent, from say particle view angle towards GR, or is it the other way around, that somehow we are living as traditional relativists with the shadows of geometry and so on, but ultimately, so to speak, the truth, the good, is in the spin 2 conception, is in the more or less particle physics conception. Okay, quick acknowledgement. Some of this relates to a joint project with Mark Baker and Smeenk on spin 2. See, for instance, also our rather elliptic due to word limit 5,000 word paper, which is especially relevant for this coupling ontology discussion we come to. And also thanks to Kian Salimkhani, who will be your speaker in 2 weeks, and we are completing for some discussions. Yeah, I will present some of Kian's work here, and he will happily probably disagree with this then in 2 weeks' time. Okay, good. Unless there are any questions with the general setup, general project, I just continue now. Just giving you an overview of what I first of all really mean by the particle physics approach to GR. Of course, we can just take GR, decompose the metric, decompose the fields, yeah, and get relative to such backgrounds, so to speak, perturbations on that background. You can do this specifically for a Minkowski background, right? Especially if we take the mother perturbations to be 0. We basically get fields Pauli at the k power to 0 order, and then we get corrections, of course. So you could say this is just a reformulation of GR, which is, however, not just available, of course, for a Minkowski background or specific beta background, but you can do it as you want and as you need it, and that's what, of course, done in practice. So this is just a reformulation, a change of variables, if you want, of GR. You can get, of course, in all kind of details about C equivalence here, but let's just describe this as a reformulation of GR for now. What you could do, however, is impose some more physical constraints, right? You could, for instance, say, if you have a Minkowski background, then there is some kind of causality condition that the metric G, right, G equals eta plus H, the metric G, is always constrained to live in the cone, so to respect the causality of the Minkowski background, right? So this, you get a much more, independent field to such a formulation, to such a degree that you might even want to call this a different theory. This is what we're going to call, or what's called in literature, by some at least. I mean, I think it's nicely worked out by Pitts and Sheaf in particular, the special relativistic approach to GR, XRGR is the following.
So sorry, what is different here from the previous slide?
Right, that you formulate this causality condition that the cone of G must always be either inside or touching the cone of eta.
So essentially, the true metric causal structure has to be weaker or strong, right? Well, it has to be smaller than the causal structure of flat space.
Yes, yeah.
So, and what is the reason why we impose that?
Okay. This is just simply a way to promote Minkowski to something more physical than just, so to speak, a variable in the background.
Why is it more physical now?
Because now it's eta it's not just a change of a variable. Now eta is really a physical constraint that says which encodes basically a certain causality structure, which is to be obeyed by every field in there, including also the G field. So
basically, so sort of setting the limits of causality or something.
Exactly. So basically, you have a Minkowski space, you could say, with all kind of fields, also effective fields, or and they all obey the causality structure, including the G. That's.
And is this always true, or is this something?
Good, fair enough. So I should say this as well. This is true. So Pitts and Sheaf argue for the global hyperbolic sector of GR. So that's, so to speak, their claim.
I see.
Yeah. So in that sense, you could say you have empirical equivalence between SRGR and GR when GR is restricted to the sector of global hyperbolic spacetimes. Okay. So that could be one conception of what you mean by kind of special relativistic approach to GR, and what we call SRGR in the following, maybe by some kind of approach which in general wants to put Minkowski first. But that's not usually what people mean when they kind of loosely talk about the particle physics approach to GR. What they seem to talk about is either something called the self-interaction approach or a gauge approach, and variants of them in the quantum. So let's start with the self-interaction approach. Here's the following. Start with the second order theory of free master spin 2. Then the guiding question is, what happens if that source is, if that field is sourced, if that theory is sourced by matter, either at the level of the equation of motion or at the level of Lagrangian. Now, the overall idea here is think of master spin 2 as a theory of gravity. Gravity is supposed to couple to matter in some universal manner, and then arguably by the energy momentum tensor. From this you get a, they call it bootstrap. Start with the spin 2 field. Now insert the matter. This is identically conserved under hitting it with a partial, which is mathematically. This thing on its own, you might say yes, because matter on its own is basically conserved energy momentum tensor, but once it gets coupled to H, it will not be conserved anymore. And from this you motivate an inconsistency. You say an inconsistency. You say this is 0, but this is not 0. Mm-hmm. And then you say, oh yeah, of course. Why is there an inconsistency? Because I forgot about the contributions of energy momentum from the H field, from the Fields-Pauli spin 2 field. So I add this, and I hope to heal thereby the inconsistency. And I keep on doing this until termination or ad infinitum. And then the claim is, upon redefining at the end, eta plus H is G, and basically we cover Einstein's field equations, and then the claims diverge a bit about how I mean, whether you get the precise Hilbert action or just up to boundary terms and so on and so forth. So it's a rough idea here.
So is the idea that any field that universally couples to matter simply by force of consistency must eventually be isomorphic to the Einstein field equation?
Yes, in a way, yes. I mean, we will come to this in a moment in a more precise way. This is, so to speak, just a holistic bootstrap at this stage. Exactly. Yeah. Okay. Yeah. I can make this more precise in a moment.
Okay.
Now, of course, you wonder what is this energy momentum tensor, especially of the H field. What you find is ambiguous, can then be improved by superpotentials, even by equation of motion terms. Normally it might not matter so much, but here in such a bootstrap where you keep on feeding this, it does matter. So we'll see later. However, there's a very nice kind of workaround to that to some extent, and also to this problem of just having to do this for infinitely many steps. It is to work not with the usual variables, second order variables, but first order variables, kind of Palatini style variables. And then actually this bootstrap consists just of one step, of just adding one correction, and then it's basically done. That's what this data showed. Okay, or argued for. Okay. Now what's interesting about this bootstrap, it's generalizes. So basically take other spin n fields and source them with corresponding Noether current. Then also you can get somehow the nonlinear extensions from that, including some ambiguities. Okay, I won't go into too much detail. This is just a sketch here, but okay. Okay, so this is this is maybe a bit quick because.
Sorry, where did the spin 2 come from at the beginning? What was the motivation for spin 2?
Okay, good. Yeah. Okay. Historically, of course, this is in the context of counting through the spins, so to speak, and realizing, okay, you have not just spin 1, spin, I don't know, 1/2 or so, but you also have spin 2, and study this field. And there can be actually given quite some arguments, for instance, that's done in Feynman's lectures or some Weinberg's lectures, why gravity has to be expressed by spin 2 as opposed to spin 1. So, for instance, yeah, and so on. So, I skipped this step in a way. You could, for instance, wonder, what if I express a field theory of gravity in terms of scalars? Does this work? What if I express it in terms of this and that? And what you end up is you have to do it with what corresponds to a spin 2 field.
So, so it's just trial and error. There's no sort of simple physical argument that says it has to be spin 2.
I mean, the argument is the argument is by exclusion, you could say.
Okay.
Okay, try and error or exclusion.
Yeah.
I guess it's some form of argument. Yeah.
There's one question online.
Yeah.
Hi there. Yeah. Can you all hear me?
Yeah.
Yeah. So, Weinberg, I don't know if he was the first to show this, but if you do this classification of spins, right, you know that the spin half integer cases aren't going to be force carriers. There's a very simple argument that you have to have integer spin to transmit forces between particles. Because if you emit a particle of half integer spin, the particle can't stay the same kind of intrinsic spin that it was. So it's going to be limited to integer spin. You can also show that it's very hard, if not impossible, at least on Minkowski spacetime, to have long-range fields with spin greater than 2. You can show that spin 3 and greater, it's very difficult, if not impossible, to get long-range fields. So you're limited to spin 0, spin 1, and spin 2. Spin 1 fields are already taken. Those are electromagnetic fields, and spin 1 fields are attractive between opposite charged objects and repulsive between like charged objects. So that's ruled out because we know gravity doesn't do that. We know positive masses are attractive. So you're really limited to spin 0 and spin 2. And then there's a really beautiful argument. So people did try to develop spin 0 theories of gravity, the Nordstrom theory of gravity. So Nordstrom proposed a theory of gravity like in 1913 when Einstein had kind of given up for a few years. But Nordstrom gravity doesn't couple to light. There's no light doesn't gravitate or experience gravitational fields, and so the deflection of light by the sun rules that out.
Nice. Yeah. Thanks, Jacob.
And thank you, Jacob. And just to add on, this is somehow sketched already in Feynman and really nicely worked out also in Orton, if you want to look this up. Okay. Yeah, sorry, some of this will be quite sketchy because I just need this material to do conceptual readings. Sorry for this. Okay, so the other big root is that of the gauge approach. The basic question here is, if I want the spin 2 field to be self-interacting, or what's worse, any kind of spin-end field, what happens to the gauge group? And so by this you can bypass discussions about the energy momentum tensor, which is always problematic because it's not really clear in this discussion which one is the right one to work with. There are various variants, and I think what's just nice to show you is the state-of-the-art result that on a very mild assumptions of locality, point covering variance, starting with something which gives them the free field limit, Fields Pauli, that you can either just have Fields Pauli's series, so non-interacting series with other series, or Einstein-Hilbert actions. Okay, I think that's very nice. Okay, so by deforming, so to speak, the gauge group of a free spin 2 field theory to get towards an interacting spin 2 theory, you're basically that heavily constrained. Okay, I can sketch a bit where this consistency comes from. If you just look at the gauge argument a la Wald, so we have the Maxwell equations, vector potential formulation with the usual current associated with the gauge invariance. If we now look for a nonlinear extension of Maxwell, so Maxwell versus F1, right? We find the following. Assume you perturb or you expand your A field around 0. Then at first order, this is the equation of motion. In second order, we have another equation of motion so the first one is for F1, the second one is for sorry. The first one is first order in A, the second one is the second order. And now taking the divergence of 10 here, we see that we get a condition in A1, which is there over and above, let's say, on 9. And so we start to overdetermine A1. And so we get a consistency problem. And only under very specific choices can we actually get a consistent theory. And so one sufficient condition here is to choose something like 13. We take the divergence of f, to be determined by earlier terms, so to speak. So if you have f of a divergence of f of n, that will be determined by, so to speak, earlier terms of f. And Walt in particular, he just drops the red term and then shows that this condition, which secures that you have consistency, can be reformulated into the existence of a infinitesimal gauge symmetry, and that upon integration gives you a gauge group of Yang-Mills, more or less uniquely. So this is, so to speak, a gauge route from saying, okay, I have a free theory of a certain spin. I want it to interact. Somehow its gauge group changes. How does it change? By the way, how it changes is highly constrained by consistency condition. And if you just, set this constraint mildly, then for spin 1, you get Yang-Mills. For spin 2, you get GR, or so this claim goes. And the state of the art result I showed earlier, this is basically in the spirit, but it's a bit more complicated in terms of mathematics, but it's also nicer and cleaner.
So, sorry, just to recap this section, so the thought is that you use gauge symmetry. So it's just at the highest level, what is are we like trying to say that GR emerges as the, sorry about that, as the unique kind of,
but just important here as a takeaway, I guess, is the linear theory has some kind of gauge structure.
Yeah.
How can we deform it? Are we free to deform it? There seem to be heavy constraints on how you can deform it, and you end up basically for spin 1 with Yang-Mills, and for spin 2 for Einstein gravity.
Got it.
I mean, sorry, this is all with some little stars and qualifications to put, but this is just to get you into the spirit of these approaches, okay? And maybe I even just quickly say something about the quantum variants, not go into detail anymore, because I want to really talk more about the conceptual readings, to be honest. That's okay. I mean, unless, of course, there are big questions here, but...
yeah, you should focus more on the conceptual things, I think.
Yeah, okay, good, yeah. And just to tell you, there is, of course, this quantum variant, of course, in the very early stage, of course, of thinking like this, just motivating why you even want to do this. We just heard it before. You talk about spins and you might think this has something to do with the quantum. Of course, in a way, not necessarily. You can just think of it also as a classical field classification. Anyway, in the quantum, so to speak, you get really glorious results, such as that you can, in the S-matrix formalism, even derives universal coupling of spin 2, so including to itself, coupling to what is then the energy momentum tensor in the classical theory. Now, you might think there's a certain dependence now here on the Minkowski background, but as then also showed by Fang, not Fang and Fronsdal, sorry, Davis and Fang, this is incorrect, as showed by Davis and Fang. Universal coupling can also be shown from consistency conservations for any background in action formalism. And so this shows that enforced self-interaction is a result of consistency of self-interaction more generally, not necessarily tied to Lorentz invariance. Okay, I will skip this very nice derivation of Huber and Deser, which is a variant of the gauge argument. And I just give you the following summary for now. So there seem to be two major ways of getting generalized from gravity to GR. To kind of get generalized from gravity to GR more or less uniquely. So this is so-called self-interaction approach, and there's a gauge approach, okay? And the take-home message for us here is these both ways work for other backgrounds as well, and for other spin 2 series. There's nothing specific about gravity as such. Okay, what I will now do is give you some takes of physicists and philosophers of what to make of these results, right?
Can you just go back to the,
Yeah.
you said there were like some take, just one, before, so, both ways work for other backgrounds. So,
I mean, the thing is, to the extent that you think these are good ways of generalizing from gravity to GR, of maybe even deriving.
So when you say gravity,
sorry. This is I guess there are two major ways of getting generalizing from Fierz-Pauli, let's say, or linearized gravity to GR.
I see. Okay.
I think the linearized dropped here.
Okay. So some way of getting from some sort of simple theory of gravity to full GR.
Yeah. Let's say there are two major ways of getting from kind of the linear spin theory to the non-linear spin theory.
And one is the self-interaction.
One is the self-interaction with this kind of heuristic self-coupling, self-interaction image in the back. And the other one is kind of the gauge root, right? And you might say to some extent they interfere. For instance, I can constrain maybe what I allow with energy momentum tensor on the self-interaction approach by gauge arguments, right? But especially the gauge argument normally runs without any kind of mention anymore of the energy momentum tensor. Okay, that's. So I think what's just important for the discussion later really is there are these two approaches, and we just keep in mind that they work for other backgrounds with the concept of gravity.
By other backgrounds,
or not just Minkowski.
I see. So you can start with any background. And
exactly. Yeah.
Okay.
Yes, and of course we can always discuss the details, but roughly, yeah. And or let's say for now, yes, we will discuss this a bit more. And they also work in spirit for other spins. So as I was saying, with spin 1 to young males.
I see.
Yeah. And this is not me claiming, this is also just in the literature itself. People do this not just for gravity, but pedagogically also for spin 1, let's say, and so on and so forth.
Is there some claim that these two approaches are the same or something? Or is that what you're going to get to?
For instance, they're closely interlinked, let's say. For instance, Fang and Fronsdal's gauge approach works by just reformulating the self-interaction approach into a gauge approach. So you make this problem of self-sourcing, this consistency problem, you make it a problem of gauge deformation. So in that sense, you can get from one to the other. So in one direction here. But then the literature is quite separated in a way. I mean, you have different papers for these different approaches. Yeah.
Okay.
But I guess this could be studied more, and I guess for now. So okay, then let's hear the more important people. Let's hear, for instance, one of the originators, Kraichnan, or maybe the originator, who wants to say that the principle of equivalence and the associated geometrical properties of GR are abundant on his approach as a foundation, and instead the starting point is taken, which employs concepts closer in some respects to those which have been found pertinent to microscopic physics, right? So that would be just how you depict this. Gupta, for instance, says Einstein himself and others have tried to construct a unified theory of the gravitational and the electromagnetic field, failed and so on. And then what he has to offer is to show that the main difference between the two theories can be attributed to the fact that while the Maxwell field corresponds to particles of spin 1, the Einstein field corresponds to particles of spin 2. Both Kraichnan and Gupta are kind of in this context of where you try to, where you had tried to unify electromagnetics, electrodynamics with gravity, and now their route is one of going all the way around, rather than taking the geometrizing route, takes the particle physics route. And I think Feynman nicely puts this, rather than geometrizing electrodynamics, just add the phenomenon of gravitation as another field to the pot, so to speak. Yeah. So I think this is a certain line which you find a lot with these approaches, just some sense of unification, some sense of putting things together. It didn't work via geometry. It works perhaps via this via the spin classification / particle physics thinking. Okay.
So the motivation now is some kind of unification.
Yeah, I mean, that's what you can, I think, extract from this quote, that there was this kind of idea of that the particle physics approach allows to see you how gravity is on par with other interactions. And not at all by geometrizing the other ones, but kind of coming from the gravity side closer to the particle physics side. So it's, And of course, unification is an extremely loaded term. What do you might mean by this? But let's just keep this also for now. We can get to systematic construction in a moment. When we look at Weinberg, we have a statement like the logical structure of physics is often anti-parallel to its historical development, suggesting, right, the particle physics approach puts the structure on its right footing. It's kind of the right, maybe accent a bit too strong to put, but that's, so to speak, fundamental from which we get to GR. So this is, of course, set in the context of this particle physics approach to GR.
So the word anti-parallel, what is that? It's just sort of you're doing it in reverse, is that?
Yeah, I mean, so historically, GR was presented to us as a geometric theory, so to speak. Yeah, and now with his reconstruction, with his particle physics take on GR, he kind of gives us the right logic as opposed to what happens in history. So that sense of anti-parallel, right?
I think
different.
He thought we shouldn't be, in general, not just here. Weinberg thought that we shouldn't be constrained to think about theories along the lines of their historical development, but ought to step back and say how we best ought to conceive of it. And he thought that about other fields too. But yes, he did not like. There's not a single image in his book on gravitation and cosmology, sort of the anti-Misner-Thorne-Wheeler.
I see.
And he really wanted to get away from the geometrical interpretation and wanted to. He believed and said, if the Einstein hadn't developed it, particle physicists would have come up with general relativity, extending zero mass spin 2 bosons on the model of what we did with reformulation of maximum.
Exactly, and I think it's very nice what you say, because of course this logic is very ambiguous. Do you mean by this, so to speak, a logic of discovery, of how I can get from one thing to the other? Do I mean by this what is, so to speak, the logic of the world from a more metaphysical point of view? These claims on their own, they have to be retaken with a grain of salt, so to speak, right? I mean, there's this, but so I just use them in a way motivationally, and then I describe the more metaphysical picture I see people have drawn out of this. Okay, Deza, for instance, also seems to stress that there is this a priori aspect of starting in his original particle physics approach with Minkowski, and that this can be removed, and you can also start with some other arbitrary spacetime. This seems to be a way of just showing of how many roads there are to go to GR, right? So so we had the aspect of unification, we had the aspect of what is the right logic for reconstruction of GR, right? And here we have this element of there seems to be really many roads leading to GR, and there seems to be kind of a concordance, kind of a robustness in these field equations. And then here's something very different, or at least as it suggests itself just from this blurb. From this point of view, Bulba and Deza write, Einstein's theory is an essentially phenomenological, albeit unique theory for describing interactions at macroscopic distances in time. So this is a very strong ontological touch now, right? Somehow GR is it's like an effective description, phenomenological description, but what's really going on is something with a spin field, so to speak. Yeah.
So that reading doesn't necessarily have to be about spin fields. It could be just a general claim about GR, because we don't have a quantum theory of GR.
Oh, right, but this is in the context of their Bulba-Deza paper. That's true. Yeah, so this is not widely taken just from what they said at some point. No, this is from their quantum derivation of algebraic field equations, which is skipped, but it's basically gauge argument. Okay, so let's come to the flow first. Dennis Linnemann presents an effective reading of G, which has broadly reductionist tones. So indeed, one of the most important achievements of the spin 2 approach is surely the recovery of the full algebraic field equations. It can then be argued that the full matrix is only an effective notion and that what remains fundamental is space-time geometry and gravitational fields separately. To be fair, Lincoln also gives a more heuristic reading later. Here Salimkhani presents at times the spin-2 bootstrap explicitly as a form of theoretic and also ontological reduction. So he says, spin-2 gravity allows for complete ontological reduction of generalitivity, symmetrical structure to meta field. So basically, this metric field G gets reduced to H, right? The words of caution, for instance, by Brian Pitts. One is about this kind of double metric status of Minkowski and another metric. But also Pitts puts forward some form of ontological rereading. He wants to say, takes the metric G, split up into some eta part, some H part. Don't think of the eta as a metric in a conventional sense. It's more like a matrix. It's a reference value, so to speak. And then this is for him still pure GR or something he called within a hair's breadth thereof. But this is now also the idea that there is something like a gravitational potential associated with the H and a reference function of the eta. And the G is also just something which is effective slash is not the basic element of how you should think about GR. What I will do now is I focus on the philosophers as the conceptual story is their bread and butter. And this doesn't mean I don't care about what the physicists have to say there, not at all. It's just that the philosophers, as opposed to the physicists, they cannot claim to just say these things in passing. It's their full-time job. Okay. If we just, and now we come to the systematic part, right? Make a long list of what could be possible readings after seeing all these quotes and and so on, and maybe your own thoughts. I think you could think in two broad categories. You could think of the spin-2 approach as some form of guided motivations for the field equations, form of rational reconstruction. How can one arrive at the field equations? How people maybe could have arrived at the field equations in the sense of an alternative history approach. You might get some structural insight about the inevitability, robustness of the field equations. Think about Mr. Sonavila's many roads, think about Lovelock's theorem in that spirit, right? On the other hand, there's this take where we take the spin-2 approach, the approach to give a new perspective about what is fundamental. Either because we claim some form of plain vanilla ontological reduction of GR, or we have some other candidates which are called coupling reduction and design reduction. And what I want to do now is focus on this second part, on this red part. I want to argue against these readings. And this leaves us with the other readings for another day, but only so much in 145-minute slot, I suppose. So reduction comes in two flavors, right? Entities and structures can be reduced to some other entities and structures, or we can talk at the level of theories. So one theory gets reduced to another theory. Typically, we run these two things together if we are interested in what the world is made of, and if we take up some form of realism, scientific realism. We don't have to. I just want to clarify this, but we will run this now because so do the discussants in this debate. Scientific reduction may be explicated in various ways. There's famously Hegelian reduction, there's functional reduction, all forms of reduction. The physicist's notion of reduction, so this is kind of taking a limit to some theory, right? Some assumption of one theory by another. That's often brought into context with this Hegelian reduction and functional reduction. And
so just to get clear, so so now that we're talking about reduction, there should be sort of two theories or two ontologies and one. So what in the spin-2 derivations, what are these two?
Yeah, that's to be clarified now. The thing is, in the spin-2 case, you either have this proposal I call the SR-GR case, where you have really a theory of its own, versus GR, or you really have some kind of theory in the sense of Fitz-Pauli you start with, but which gets morphed into GR. And that seems very, the latter thing seems very difficult to grasp with the standard notions of reduction.
Yeah,
and that's what I'm getting at.
You're getting it, sorry.
Yeah. So the thing is what we saw as a so-called derivations. These are formally generalizations where the ambiguities get kind of killed off by some constraints, no matter how mild they are. So this is clearly no reduction in the physicist sense of limit or so. That you might say it could perhaps still be construed as an Argelian or functional reduction. Let's take a look at the Argelian reduction. The problem here is, sorry, I'm jumping a bit, I'm going a bit quickly now, but the problem is that neither the bootstrap nor the gauge argument work as a direct logical argument as you would have it in an Argelian reduction from one theory to the other theory, together with some bridge laws which connect the variables. So the idea of an Argelian reduction is to one theory with certain vocabulary, you connect to some other theory with some other vocabulary, via some bridge laws, say statistical mechanical kinetic gas theory to thermodynamics. And this is not what you're doing here. Instead of saying masters Fierce-Pauli plus bridge laws entails GR, what you're really doing is Fierce-Pauli's plus some constraints generalized uniquely to SRGR, and then maybe SRGR plus some bridge laws entails GR. And so that's why we cannot really use this form of reduction. So you might say SRGR differs from GR, and so maybe the claim is about that somehow SR of GR allows for reduction of GR, but this is really just GR for a sector. So not so interesting. But it might be that we're overlooking something. We might think too much inside the usual boxes. One might be able to put some flesh onto the logical reduction story or provide one in a rather different sense. And that's the aim in the following with the proposed dynamic and design ontologies, respectively. What do I mean by this? So the idea of a dynamic ontology is, think of GR as really fundamentally as describing some coupling of a spin-2 entity. A process that gets only mathematically represented through a metric description. So call this a dynamic ontology, as the focus is really on interaction, process of coupling. So this might make it more attractive to think of something like SRGR, which just looks like after all this expansion of GR, as something more fundamental than GR, because now you're kind of really stressing this dynamic element, that you have this spin-2 particles coupling to each other. This gives rise to something which I can represent nicely mathematically, but there's still some physical mechanism I'm not capturing if I just say at a geometric level. Okay, such interpretation relates very much to this self-interaction approach. One immediate consequence of having such a dynamic ontology view is that if we really go through with this, then we would also have to formulate, at least you would think, so to speak, by coherence, for other theories, such as Young-Mills. You should think of Young-Mills as a self-interacting spin-1 field, and so on and so forth. So here I think one can also enter with a dilemma, which we formulated in a paper some years ago already. So on the self-interaction approach, it's either unclear to which of the many possible stretched energy tensors the field should really couple to, this is ambiguity, or if you don't really think of coupling at the level of equation of motion, but just at the level of the field itself, just brutally somehow, it's unclear why it should be a coupling around Minkowski spacetimes. Why is it somehow okay to assume Minkowski as a background if you have the energy momentum tensor horn, if you think about coupling of the H field to the energy momentum tensor? Well, admittedly, for flat spacetime, the notion of energy momentum tensor conservation is somewhat preferred. There is genuine conservation and just covariant conservation. So, yeah, the problem here really at the end of the day is just, and I think I will skip some parts of this, that first of all, if we were to do the self-interaction approach, how would we ever find the right energy momentum tensor? How would we do that? And then the logical question is really, to what extent is really this energy momentum tensor which you really need? Is this a linearized form from GR? Is this really a natural flat spacetime object? Because the claim is, right, you're starting with some kind of flat space-time environment where you're coupling to your own energy momentum tensors, and so you would expect this energy momentum tensor to stand for a standard flat space-time energy momentum tensor. But as it turns out, the technical result is oops, this was a mistake.
Give it a second.
There we go.
I think it works again. It's just
Let me just share the screen one more time. Just a second, where are the slides?
Perfect. Thanks.
yeah. So maybe, I hope this is not too quick, but I mean, I still have 50 minutes or 10 minutes?
About 10 minutes.
10 minutes,
Yeah.
okay.
If you want to leave some time for questions,
Yeah.
you might want to.
Yeah, okay. Okay. Oops.
We can go a few minutes over because we
Yeah.
started a bit late, but probably not too much.
Yeah, so maybe I just go one step back just to tell you exactly. So so we have this dilemma again, right? We have this either the option we're coupling to the energy momentum tensor or to the H field itself. What's strange is on the second horn, which why would somehow the flat background be preferred? Why don't you have basically an ontology now somewhat fragmented, where there are all kind of different stories true at the same time of self-coupling with respect to that background, self-coupling with respect to that background. Okay, so that seems unattractive. So therefore, look at the first horn, where we are at flat space-time, because at flat space-time we at least have a good sense of conservation of energy momentum tensor. But there the problem is we don't have a good sense of what is the right energy momentum tensor, just from special relativity theory or just from the Minkowski background. And it turns out we really just need to take the energy momentum tensor from GR, and nothing else would normally become a standard energy momentum tensor to get to the right result with the bootstrap. So the object, so to speak, at play in this interaction approach is neither a direct Lagrangian-based neutral current nor the commonly corrected symmetric Lagrangian-based neutral current. It results from some form of additional manipulations. And so, of course, we have this epistemic question how to get there, but ontological questions really, to what extent such a story where we take the background of flat space and afterwards it's more fundamental, can we live with having such a notion of energy momentum tensor which is so detached from such a space-time structure, which is not the original, how can we live with energy momentum tensor which is not a sensible energy momentum tensor in the usual specialistic senses. I could, of course, revise what we mean by energy momentum tensor, but then we get, of course, a fine-tuning problem. And okay, so that leaves this this ontology, and just want to quickly go through the other option, just maybe mention it. That is it of a design ontology. Okay, so maybe there's really no way we can talk about these bootstraps or gauge arguments as some form of meaningful reduction or dynamic ontological reductions or something like this, right? Maybe that's not how we should understand it. Maybe the idea is think of ontology different. Think of ontology in the sense of how you think about design models as opposed to structure models. So what is this supposed to mean? So I can give you a model of a cake. They say, here are the ingredients, that's how you bake it. This is a design model, this is the way how you construct, design a cake. And I can, of course, also from the perspective of the eater of the cake say, oh, there are these layers, or from the perspective of the food engineer, there are these proteins in the cake, and that would be the structure model of the cake. And maybe the idea is what we're getting with some approach like the particle physics approach of gauge argument and the bootstrap. What we're really getting is some kind of design model / design ontology. So, and my claim would be that Salimkhani's book, the day, is best construed as providing such an ontology. So you would say, care about what is fundamental, not what exists. what is fundamental, what is derivative? Well, particle physics derivation, so what we just were looking through, the gauge argument and the self-interaction argument, they show you that H is more fundamental than G, because H builds G, namely via this recipe of taking H, putting it together with some matter, self-coupling, or gauge, extending the gauge group, and you get, and thereby you get G. And in fact, Salimkhani also uses this pie metaphor. If I mix flour, butter, and sugar and bake it, I obtain a traditional British pound cake. If I start with some ingredients plus lemon juice, I obtain something else. Okay, so of course we could read like Salimkhani then, and we could read Salimkhani as proposing the ontology. The question, of course, to what extent is this really satisfactory? Well, a design ontology changes strongly what we mean by fundamentology in the usual structural sense, right? So normally when we are, if it's doing metaphysics of science, what we mean by an ontology is somehow basic structure of reality. It's a bit naive, but something, you're looking for something right, something absolute, maybe even something non-contextual, something interest independent. Maybe this is all a bit naive. But especially when it comes about how to design something, you would wonder why there should be then a sense of unique, right ontology. There seems to be many good ways to design something. And so it's true for GR. There's a good way to design GR as many different ways to design GR as a spin-2 generalization. For instance, we're looking also at causality obstructions. There's a good way to define GR as such, for instance, by the EPS exponentization. And so it seems a bit strange to single out GR for discussion on design ontology, because design ontology seems to be something which you really, first of all, would have to argue for itself as something as an attractive position to say why something is fundamental or not. And at the end of the day, I would just think the design ontology, in the way how I would construe it, is after all not so different from a rational reconstruction. So we would, in that sense, say we come back with the design ontology to the epistemological road. Okay, then I will wrap up here now, so we hopefully have 3-4 minutes for questions.
Yeah, let's do that. Okay, so thanks.
Should I just summarize this?
Yeah, let's do that.
So I wanted to do a demystification of the spin-2 approach. Not sure everything cleared up. Maybe more questions arise now than they were before, but that would also be a success in some way. In particular, I wanted to put its ontological readings under scrutiny. Yeah. So as opposed to what we learned from this question was, so to speak, to what extent, as opposed to what extent can we think of just learning about GR from particle physics approach? The question was, to what extent can we really think of this renders us, whether something else is fundamental with respect to GR than we thought before. So, and I think there are really 2 lessons here. One is how to think of the possible conceptual takes of spin-2. That is, we should think of it epistemologically. And another more general one is it also raises all kind of interesting discussions of what you even mean by ontology and how good this distinction between ontology and epistemology can be, because certain forms of doing ontology actually blends over into epistemology after all. And I think this design ontology was a good example of that. Okay, now I conclude with this, and thank you everyone for this attention.
Okay, we have a few minutes for questions in the room. Peter.
So I have a somewhat pragmatic attitude towards ontology in the sense that we have a long tradition of looking at theories that can be formulated in alternative ways. Ernst Mach did it for mechanics and helped define what we mean by classical mechanics by showing the interconvertibility of the different formulations, Hamiltonian, Lagrangian, virtual displacements. I mean, and the same Poincaré wrote extensively going back and forth between the different ways of formulating electrodynamics. And, by now, Maxwellian theory is understood in a myriad of ways, and not nobody, but it's increasingly, I think, accepted that Maxwellian theory isn't about fundamentally one rather than another formulation of the theory. Now, conversely, there are cases where something that looks interconvertible at that level, like the path integral formulation of quantum mechanics, comes not at the time when Feynman first formulated it, but in the development of quantum field theory more generally, to be ineliminable in any practical way. You know, I mean, someone could say, well, in principle, we could do quantum field theory without path integral formulation, but in real life, you can't. Or people used to say, well, we could do general relativity without non-Euclidean geometry, but no one's ever come up with a plausible way of doing that for any realistic work that's to be accomplished. So it seems to me there are two kinds of cases. One where you choose the formulation in a kind of fluid, ambidextrous, or multidextrous way to solve the problem at hand. Sometimes it's better to work with Hamiltonian, sometimes it's better to work with Lagrangians, right? If you want explicit relativistic invariance, you use Lagrangian. But there are lots of, we haven't abandoned using Hamiltonians, we use them all the time. Whereas other cases, it seems to me at a certain point, the practical uses to which we want to apply this make other formulations awkward and imaginary in some way. Like, you could do it, but no one knows how to do it. And so the question that I would have here is, at a certain point, it could be the case that doing general relativity, or whatever one calls the generalization of the theory, to be done with spin zero massless particles and, you know, perturbative expansion around, you know, H and so on. When that happens, then I think you could settle the ontological question, or at least in a pragmatic way say, general relativity is non-Euclidean, or the path integral formulation is not just switchable to one of the zillion other formulations of quantum mechanics. So, I mean, I mean, it seems kind of paradoxical to say I'm a pragmatist about ontology, but that, sure. I don't think that's as oxymoronic as it sounds.
I think that's
no, yeah. No, I think this is, in a way, quite a standard way of how many philosophers of physics think also. They're not very deeply interested in this kind of more metaphysics of science way of talking, and exactly have more this sense of ontology, which is about sorting things, and this can be interest, context dependent even, right? I would just want to highlight one thing. So for instance, take Maxwell's theory. Of course, there are the different formulations of Maxwell's theory, and we can argue whether there's something interesting going on, or whether there's all the same sides of the same metal, or the different side of the same metal, right? But then if you take something like Maxwell's theory and Young-Mills, right, you normally have something to say about that one thing gets reduced by the other, yeah? And so no matter what are these different reformulations on each side here, there's some interesting story of how they connect, right? And I think that's where I see the parallel here with spin 2 and, I mean, in the sense of Piers Pauli in particular, right? And GR, the bootstrap somehow seems to enforce GR. You can definitely differently represent GR, Einstein algebras, or I don't know how you want. But somehow what seems to remain is this point about, in some formulation you can get from some very different theory to GR. And of course, normally the straightforward take would be, yeah, okay, this is a lesson to say simply this reduction can reduce GR to this Piers Pauli theory. But what I find attractive in this discussion is some people have tried to resist this obvious point and try to go the other way around. And I guess that coupling ontology and the sound ontology take is just an attempt to kind of be charitable to that. There's, after all, a very attractive intuition about something mechanical happening, something dynamic happening on this dynamic ontology. And also with the sound ontology, I think this is a way to appreciate at least something of this relationship. But I agree, of course, in many contexts, one should maybe think more about, first of all, theory equivalence, issues of conventionalism, also pragmatic takes and so on. But I hope that this is still, so to speak, to be justified as a project in addition to what you were saying. So yeah, that makes sense. Yeah.
Very good.
Any questions online? We can do like one quick question if anybody wants to ask something. If not, I mean, I have questions, but I think I will, in the interest of moving on to the colloquium, thank the speaker again. So we don't have a foundation seminar next week because it's President's Day. And then we'll resume on February 23rd. Thanks, everyone.